Hello everyone, and welcome to lecture number 8 on IPv4 addressing. Last time we finished up our discussion of TCP by talking about congestion control. And congestion control is a way to control the rate at which TCP participants send data to prevent overwhelming the network. It's implemented by dynamically controlling the size of what's called a congestion window, which is the upper limit on the number of packets that you can have in flight. Which is a measurement of the amount of load you're placing on the network. It's controlled by heuristics. We talked in detail about the Reno style of congestion control. That operates in 3 phases. It starts off in slow start, where there's exponential growth in the size of the TCP congestion window to allow the throughput to grow exponentially, so it doubles repeatedly. This allows you to quickly find the maximum capacity of the network because you're doubling every time. It allows you to get to any number arbitrarily quickly. Not arbitrarily, but in log time. After all these congestion control, not all of these, but TCP Reno congestion control and traditional TCP congestion control relies on observations of packet loss as an indication that the network is congested. So when there is a packet loss after slow start, when you send too many packets, you move to another phase called congestion avoidance. In this phase, you linearly grow the size of the window. So you increment it slowly and by constant factor for each round trip time, which slowly increases your throughput until eventually you again overwhelm the network. And at that point, you move to fast recovery, which causes you to cut the size of the window in half. So it has this sawtooth style shape of congestion window, moving between half the maximum capacity of the network and the maximum capacity, assuming the network is static and has a fixed capacity, giving you overall 3/4 of the maximum theoretical throughput on that simple model. This TCP Reno style congestion control has additive increase in the congestion window in the steady state and multiplicative decrease. So you bump it up by a constant, that's the additive increase, and multiplicative decrease is when you cut it in half. Doing that ensures fair sharing among multiple connections or flows, as we call them, on the network, which is a very important feature of TCP Reno and classic TCP congestion control. We also saw a couple of alternative designs for TCP congestion control. We saw both briefly Cubic and BBR. Cubic had a different style. Instead of additive increase and multiplicative decrease for changing the shape of the congestion window, and BBR uses not packet loss to control the congestion window, but changes in the round trip time. So it tries to actually accurately look at small details in the round trip times to indicate that queues are getting long in routers and reduce send rates when that happens. So that avoids packet loss, actually, which is pretty cool. So in addition to that, there were some minor details on TCP I talked about, in particular because TCP actually provides a ton of functionality and it hides a lot of details about how retransmissions are happening and how chunking is happening. Hides all that from the application. But some applications actually want to control that stuff because not every different applications have different requirements. So socket options are a way for the application to control a little bit of what TCP is doing, break that total abstraction and make it not a black box but more of a gray box. So for example, Nagel's algorithm merges consecutive small packets to reduce the overhead of headers. So if you're sending just a little bit of data, every packet has a certain amount of header overhead for both the IP addressing and the TCP segmentation and whatnot. You don't want to have all that overhead for just a small message, so Nagel's algorithm combines those, but that increases latency. There's a trade-off there. Some applications want to do that, some don't. Socket options give you the way to control that. I also mentioned briefly TCP keep alive messages to have packets exchanged even when the applications are sending no data. All right, but we're going to have a couple more slides here to wrap up TCP, and then we're going to move on to a different topic. But last time I talked about TCP Reno in detail, a little bit about BBR and Cubic. There are lots of other options as well, which have different trade-offs and have different levels of adoption, popularity, and different fairness guarantees as well. So when you do your Wireshark lab, for example, you might be surprised to see that the behavior you observe is not what is documented in the book, because the book talks about TCP Reno congestion control. So I did some traces on my own machine to look at what happens in practice, at least on a MacBook these days. So I started up Wireshark and did an HTTP post of a small file using a wired Ethernet connection, so Thunderbolt Ethernet interface on my MacBook. And this plot is what's called a like Stevens style TCP sequence number plot, which you can get in Wireshark, and it shows the sequence numbers that are used in the flow that the sent data has over time. So X is time and Y is sequence number. So basically Y is the amount of data sent so far, and X is time. So over time, you're sending more and more data. So you're always going to move from the lower left 0, 0 up to X, Y, where X is the amount of time and Y is the amount of data sent so far. It always goes upward. It's cumulative. So I want you to look at this plot and tell me what's happening here. Why is it shaped like this? Okay, for an HTTP post on sending a small file. Stop and think about that. So what I hope you see after looking at this is growth in the window size, probably due to slow start in TCP congestion control. So we have an initial window size. We send some data and then we stop because the window we reach the window size, and then after one round trip time, we send some more data this time. We wait again, send some more data. The amount of data we send kind of grows. It looks like doubles or almost doubles each time, which is slow start. Okay, and it takes a while. So after 280 milliseconds, it's still growing. So it takes a while for this connection to reach its maximum speed, and it probably didn't ever reach the maximum speed available that would be possible on this connection. Here's another example where I did the same action. So again, I'm posting a small file in an HTTP request, but I'm doing it on Wi-Fi from the same computer. And the plot looks a little different, right? There's like the packets are not sent all in bursts, but there's like a little bit of delay between the first part of the window and the second part sometimes, or multiple delays. So I want you to stop and think, well, what might be different with Wi-Fi here that causes it to behave this way? Well, it's hard to know, actually, and I don't have a solid answer, but it might be that with Wi-Fi, we'll learn later that there's a greater chance of interference. So the radio might detect at given times that there are other senders on the channel, so you have to wait your turn to use the radio spectrum. That could be what's happening here when there are these gaps. That's my most likely explanation. That the carrier sensing, which we'll learn about later. I mean, some other radio user at these times is using the airspace, so to speak, the radio spectrum, and so we have to wait. So even though we can send at this time, we wait because the local link is not available. So end to end, the network is not congested, but maybe the first hop is congested, like just the Wi-Fi radio has to wait. Okay, here's another scenario. I'm back on the wired connection, same computer. This time I'm using the SCP program, which is command line tool for transferring files between Unix machines. And I'm transferring a large file to a server that is in Seattle. So from Northwestern to Seattle over a wired connection, I get this behavior you see here. So there, you can see in the middle, there's kind of a slow starty thing, but then early on, there are a lot of small bursts, and later on, it kind of saturates and sends at a constant rate. So this is quite different. I want you to stop and think about what might be happening there. Okay, so two different things. So at the beginning, I think we can explain this by the fact that SCP the SCP process involves probably some authentication. Like when I when I connect to a server to send a file there, I have to send it my username and password, and it has to give a response that acknowledges that. Before that happens, it probably has to negotiate what style of encryption it's using. So there are a lot of little packets. So at basically the beginning, the slowness at the beginning is explained by the application being slow. The application having actually a lot of small requests to send back and forth to set things up, like exchanging the password. Once it gets to time, 1 second, I think that's where the file transfer actually starts. So at that time, we want to send a lot of data, and we do that. We start sending more and more data with slow start. Eventually, there's a packet loss. Well, actually, there isn't. So what happens is eventually we reach a constant where maybe TCP never dropped a packet, but we're limited in the rate of data we can send. If you look at the slope of this line, we try to calculate the slope, we'll see, let's say between here, the 3 million bytes and 9 million bytes. So we have 6 million bytes on this y-axis in this gap here. On the x-axis, how much time do we have there? Roughly 1.4. We have roughly half a second. So 6 megabytes in half a second. I think so. 6 megabytes times 8 bytes per packet divided by half a second gives us roughly 100 million bits per second. So the slope of this line is precisely equal to 100 megabits, which I happen to know is the maximum speed of many Ethernet connections. So what's happening here is that in my office, the maximum speed of the port in the wall, like that Ethernet wire, is limited to 100 megabits per second. So actually, TCP, there's no congestion in the network at all. TCP congestion control doesn't do anything because I can't even send data from my computer to the first hop at a rate fast enough to overwhelm the network. I'm getting a very good connection from the Northwestern campus to Seattle. This machine is actually at Amazon Web Services, so it's in a big data center and it has a fast connection. Okay, so that was a little tricky, right? But pretty cool observation. Pretty cool that we were able to notice the precise data rate from the slope. One final variation, so the same thing, SCP transfer of a large file on campus. This time it's on campus. So I'm not transferring from here, from Northwestern to Seattle. I'm going from Northwestern to Northwestern. And the pattern looks a little bit different, right? So stop and think about what's happening here. This one, to be honest, I have a little less insight about. I can still see that the slope here is about 100. I think the slope here is still saturating at 100 megabits per second. So that there's still that local link that's the upper bound on the throughput of the rate of data I can send. But then the absence of slow start here, and still, again, at the beginning, there's probably some kind of password authentication, connection setup stuff that is application layer delays. But the absence of slow start here is pretty interesting. So the connection immediately goes to sending at a very fast rate. And that I can't explain except for suggesting that the TCP implementation is not doing TCP Reno, or it has some special case rules where maybe if the endpoint, notice that the destination IP address is very close to the source, so it can actually tell based on the closeness of these numbers and the subnet, which we'll talk about today. The implementation of TCP can actually probably tell that this is on the same network, that it's not going through any routers, only through switches, and therefore there's unlikely to be congestion. And so therefore, just send at the maximum rate, right? So that could be the rule that's kicking in here. All right. Cool. So I hope that was that wrapped things up and was insightful. Okay, so TCP was a big topic, but we're done with it now. We're going to move on to IP, Internet Protocol, and forwarding. Okay, so the topic of IP, that layer of the network, which is an important one, I think just as important as TCP, perhaps even more so. It's broken into 2 chapters in the book, which are described often as the data plane and the control plane. So we're going to start with the data plane, which is about forwarding packets, and later on the control plane we'll talk about like determining forwarding rules. But we're looking now at the core of the network, looking in detail about what these routers do, how these routers make decisions to somehow get packets between all the different edge locations in the internet. All right. So we'll come back to this diagram of the layers of internet protocols. We're looking now at this green one, which is the IP layer. Inside of an IP packet, we would typically would have a TCP segment, which has all the TCP stuff that we talked about recently. And inside that, you might have, for example, an HTTP request or response broken up perhaps among many consecutive TCP packets. But the key thing here is that we're wrapping up a TCP segment with some additional information, in particular an IP address of the destination and source. We'll see the details later. And the purpose of all this information we're adding above TCP is to give the necessary information to route the data from a source to the destination going along many hops. Okay, so that's an important problem on the internet that we haven't talked about yet. How do we navigate the internet, literally? That's what we'll be dealing with here. And the internet protocol, IP, is responsible for delivering packets. They're often called datagrams at this level, although I tend to use the word packet for every layer of the stack. So again, these are kind of like postcards. They have an address, they have a little bit of data, they're limited in size. The maximum transmission unit, or MTU, is the size limit for datagrams. Usually this is about 1.5 kilobytes, 1,500 bytes. And on the internet, using the IP protocol, we have best effort delivery, meaning that packets can be dropped. This makes the operation of routers easy. If their queues are full, they just drop the packets. They don't have to worry about like storing it or telling the sender that there was a problem, anything like that. It just does something simple. Okay. We've kind of said all that already in the past, but now what we're going to talk about is how packets reach their intended destination, navigating this very complex, huge network of routers and links. Okay. The term we have for that is routing. That's why these things are called routers. Okay. So routing is the process of guiding packets to their final destination. This is done by routers. That's the main purpose of routers. We use this diagram, this symbol for routers, which kind of shows multiple connections and interconnections between them so that things can flow any way they want through them. And solving this routing problem involves two parts which we often separate. So I mentioned this at the beginning of this section. The data plane is what we're talking about here, which is implementing forwarding rules for packets. When a packet arrives, sending it off in the right direction. But deciding those forwarding rules at each router is done by the control plane, which is a different the BGP protocol and other routing protocols are used for that, and software-defined networking is another approach for doing that in a centralized manner. Well, anyway, we'll talk about the control plane later, like figuring out what the best paths are in the internet. We're going to start off, though, assuming that somehow each router knows what has a set of forwarding rules that it can use for packets. We'll kind of see how that works operationally, and then in the next step, in the next chapter, we'll see how to optimally decide those rules in a decentralized manner. Okay. But just to see what routing means in an illustration, we have a sender and a receiver here, and they're sending packets. The packets have multiple headers at different layers. We're looking at the network level. With IP layer is called the network layer because it involves dealing with the multiple hops of the internet, which is what the fact that there are multiple hops connected together is what makes it a network. So each of these routers doesn't know what's happening end to end with the packets. It only knows what's happening in its neighborhood. It has rules for forwarding packets. It doesn't establish connections end to end or do anything end to end. It just sees packets come in and forwards packets using its rules within its neighborhood. So for this particular router that's highlighted here, it only controls its own behavior. It only knows about the 4 links that it's connected to directly, and who, I guess it also communicates with those neighbors on the other sides of those links. But it receives packets on those links, and it forwards packets along any one of those links depending on the rules that it has. Those rules, of course, have to be defined correctly. We'll talk about that later, like I said. But this decentralization is kind of elegant. And that's a central feature of the internet. Okay. What exactly is a router? I mean, we're using these silly round, flattened disk diagrams for them, but in practice, they look like some of these images you see here. A router is a device with multiple network connections or links that's dedicated to forwarding packets and also deciding forwarding rules. But we'll talk about deciding the rules later. But for the purpose of this chapter, it's implementing forwarding rules to forward packets. So there are small routers and big routers. So an edge router is a router with just one connection to the internet, and then connections to end devices that are going to supply traffic and receive traffic. So such as the router that you might have in your home. This is a slightly bigger router, but still a pretty small one for like a small office or something. But what you see here in this middle image is that routers usually have slots where you can connect different types of electronic modules to connect different kinds of cables. Like these slots, when you unscrew these screws and remove the plates, you can put in a fiber optic module or an Ethernet module. Different kinds of fiber optic modules, different kinds of Ethernet modules, and so on. You might even be able to put in a wireless radio into one of these slots, depending on the router. Because, in fact, the internet has many different kinds of links. On the far right-hand side, we have a huge, like rack-sized router. This is like what you'd see in the core of the internet. And a router like this can handle up to 160 terabytes per second. Last I checked, which is just a huge number. I mean, if you think about the amount of data flowing, that amount of data, a CPU, by contrast, can do tens of gigabits per second, I think. So this is like 1,000 times more data flow in and out than you can get on the latest CPU using all of the PCI Express pins that it has. So you might wonder, how is it possible to have a router that does 1,000 times as much data transfer as a CPU? I mean, we're all impressed by how fast CPUs are, or we should be anyway. The answer is, of course, there's a lot of parallelism built in, and that's why this machine is so big. There are a lot of ports. You can see in the bottom a lot of plugs. Each of those plugs is hooked up to a different processor to handle stuff in parallel. Okay, so the rules, this router might be sharing a single set of rules, perhaps, for deciding the forwarding, but those rules are implemented in parallel on a lot of different controllers or microprocessors, depending on how you want to think about it. All right, so let's dive into this. The first thing we need to understand is how addressing works on the internet. We're going to be talking about IP version 4, which is the version of internet. There probably was a version 1, 2, and 3. I've never seen them, but IP version 4 is what became popular when the internet grew into a global network. So I think this is around in the 80s and later. So with IP version 4, we have IP addresses, which are 32-bit numbers that are expressed in dotted quad decimal notation, like something dot something dot something dot something. And the numbers between the dots are decimal numbers between 0 and 255. So they correspond to 8 bits each. So there are 4 of them. So 4 times 8 is 32. So that's the 32-bit number. So you can an IP address expressed with zeros and ones with bits might look like you see here on the lower right. To express it in human readable form in dotted quad notation, we break it into 4 equal sized pieces of 8 bits. Translate each one of those to a decimal number. You can see that these are ones, and this first one is apparently 223, and so this becomes 223.1.1.1. Okay, I'm not. So this dotted quad notation is kind of annoying actually, but it allows you to write something that can be pretty easily translated to binary without having to know what hex is. I mean, hex is a much better way easier way really once you learn it to translate from a condensed format into the long series of zeros and ones. But not everyone knows what hex is, so I think that's why they went with the dotted quad decimal notation to make it more accessible to like IT people and users of the internet. Okay. On an IP network, we have we refer to the connections, the computers, as interfaces. So every connection is an interface. A computer can have multiple connections. So that's why we distinguish between hosts and interfaces, because a single host can have multiple interfaces. This pink, orange machine down here has both a wired and a Wi-Fi interface. Each of those interfaces would have different IP addresses, and they each could be connected to different parts of the network actually. Like for example, the wireless radio might be connected to a base station down in the bottom here that's connected to this part of the network, whereas the wired connection might connect to this part of the network. And that's one of the reasons why they have different IP addresses, so that using the wireless radio, this bottom one can communicate to this part through this part of the network, or with the wired connection through this upper part of the network. Routers usually have multiple interfaces, multiple links, and so they have multiple IP addresses. So this router in the middle has 3 IP addresses corresponding to the 3 interfaces it has, and we'll see later on the 3 subnets that it's connected to. So this router is actually serving as an intermediary to direct traffic between all of these 3 what are called subnets. We'll get to that in a second. So this diagram shows a router in the middle. There also is another kind of connective device called a switch, which I'm showing here with a box-shaped pizza box kind of thing here with an X on top. That's a switch. So the purpose of a switch here, we'll learn more about these in let's say 4 or 5 lectures. A switch accepts multiple wired Ethernet connections and allows the traffic to flow between them. Basically, it routes. It shouldn't be called routing, but it switches. It forwards packets that arrive in one of the ports to all the other ports, the appropriate one of the other ports, which is similar to a router, except it's less intelligent. So we'll talk about those later. You can think of these these switches for now as just making kind of a physical connection between all of these links so that packets flow to everyone else here, whereas the routers receive a packet and make a decision about where to send it. Okay, so we have switches for connecting wired Ethernet users nearby. We have base stations to accept wired connections, multiple wired connections, and we have cables for point-to-point connections. Cables in this case are connecting the end hosts to switches, and the switches to routers or other switches, or routers to routers could also be connected with cables. We're going to talk these low-level details of like switches and base stations and wires and stuff. We're going to talk more about those later. I just want to give you a little bit of an introduction here, so enough to understand what's happening with IP. And part of that preview I want to give you is MAC addresses. So we just introduced IP addresses. I haven't really showed how they're used, but I want to quickly tell you about a different kind of address that's used for devices on the internet, which are MAC addresses. So MAC addresses are used just for local communication when you have devices on a shared channel. And MAC addresses are factory coded. So your machine has the same MAC address all the time. It's pretty long, so it should be different than any other machine's MAC address. And it always stays the same. So whenever you join a network, you have that to start off with. And you use that to distinguish between the other hosts, the other interfaces that are on the same channel. So this switch here in the middle is connected to wires running to 3 computers and 1 router, so four interfaces in total. Let's imagine that what the switch does is when it receives a packet, it just sends it to everyone else in this subnet. We'll define a subnet in a second. But yeah, subnet is a set of machines that are connected directly, that can communicate directly without going through a router. So these MAC addresses are used to identify whether the packet sent locally on this shared channel through the switch is destined toward which of these four. It identifies which of these four interfaces a packet should be received by. So if, just to make it more concrete, if this machine on the left wants to send a packet to the router, like through the router, it has to put the MAC address of the router as the Ethernet MAC address destination for that packet. Ethernet is like a layer below or above, depending on how you're thinking of IP. But that's just a wrapper that changes at each hop. Okay. I'm not sure that was helpful because we may be getting a little ahead of ourselves with MAC addresses, but that's that. Let's get back to IP. Okay. So to understand routing on IP networks, we need to first define subnets. So subnets are chunks of IP addresses that can communicate directly without traveling through a router. This picture shows three subnets. So we have one router in the middle. The router is responsible for handling traffic between these three segments, but traffic that is flowing within these segments does not have to go through a router. It's within a subnet. These machines can communicate directly. So for example, this machine at the top that has the address 223.1.1.1 can send a packet directly to 223.1.1.2 without, it can just send the packet with that address on it. Actually, it needs the MAC address. We'll talk about that in a later chapter. That's just a detail. And that'll go directly to this packet. There's no routing involved. It doesn't go through a router. There are no rules needed. This machine just knows that this other machine is connected to the same interface, and therefore it can send a packet directly to it. Right? If everyone's connected to everyone else, then sending messages is easy. You just kind of send it. You can just send it directly. There are no decisions that have to be made about what path to take because you're actually connected directly to the receiver. And so yeah, a subnet is a group of machines that are all connected directly to each other. So these three plus this fourth one down here are on one subnet. This bottom left machine actually has two interfaces, and so it's on two subnets. And the routers actually straddles three subnets. The three different interfaces of the router are part of the three different subnets. Okay, so because this router has an interface that's on the upper left subnet, that means that any of these machines can send a packet to the router. And because the router also is connected to the other one, but the fact that this router is connected on three different subnets with three different IP addresses means that it can receive packets from any of the three and then forward them to any of the other three. Whereas these other machines have no way to directly communicate to the machines on other subnets because they don't have a connection on the same subnet. They use the router as an intermediary to reach these other destinations. Okay. Subnets are defined are ranges of IP addresses, and they're defined by subnet masks. So you have a range of contiguous IP addresses. If you look carefully, you'll see that the numbers of these IP addresses in the same subnets are all pretty similar. They only vary in the least significant number, like the bottom number is different, but like this one in the upper left is the 223.1.1.1 subnet. Excuse me. Whereas the one on the right is the 223.1.2 subnet. These are all .2 then something, and then the bottom one is the 1.3 subnet. And the subnet mask indicates a bit position where the subnet where we split the IP address and all the bits higher than that position define the subnet, and the ones below define the individual machines within the subnet. And I'll have a diagram in a second that shows that a little bit more explicitly. Okay, but in this example, we have a bunch of /24 subnets, which means that the highest 24 bits of the addresses identify the subnet. So if you have another IP address and the top 24 bits are the same, which is true of these three machines, for example, then they are on the same subnet. But then if the one of the high 24 bits is different, that means it must be on a different subnet, which means that you have to send the packet through a router to reach that destination. So there are two ways to express subnets. One is with this CIDR notation, which has slash and then a number, which just says the number of bits. That's the simplest and I think preferred way. And another way you might see is as a bit mask, which is like translating it into something that looks like an IP address, like 255.255.255.0 is 24 ones followed by 8 zeros. And that's equivalent to /24 because the /24 is the 24 ones at the beginning. This bit mask can be kind of ANDed bitwise with an IP address to get the identity of the subnet. So why do we have subnets again? This seems pretty complicated. What subnets are used for is to decide where a packet needs to be sent, whether a packet can be sent directly to the destination or it needs to go through a router. So if the destination IP address is in the same subnet, you can use that subnet mask I just mentioned to decide whether that a machine is on your subnet. Each subnet has a mask to define the size, like the range of IP addresses that are in there. If the destination address for a packet is outside of your subnet, then you have to send it to a router. And the router will relay it somehow. It'll figure out what direction to send it to reach the final destination. This will become a little bit more clear after that link layer chapter 4, where we talk about MAC addresses and ARP and stuff like that, which tells us more clearly what's happening between these neighboring machines. But at a high level, let's just say that these machines, if they're on the same subnet, can all talk to each other directly. Okay. So here's an example we can look at and think about to try to see if we understand subnets. Here's a network. I mean, I'm showing a slightly more complex network. There actually are 3 routers, still, of course, not a great simplification compared to the internet. And we have some edge hosts, some hosts at the edge, and there's several subnets here. I want you to count the subnets. Stop and think about that. Try to count them. And remember that subnets are groups of interfaces that can communicate without passing through a router. So which of the interfaces, how many clusters of interfaces can you find here that can communicate without going through a router? And each of those is a subnet. So try to identify those and count them, and let me know what you see what you come up with. All right, I hope you did that. So the answer actually is 6. I hope you found at least 3. So these 3 machines plus the router at top, those are all connected directly through wires. That's a subnet, and the IP addresses are all contiguous. Then also 2 more on the bottom in a similar arrangement. What's less obvious is that these links between routers are also subnets themselves, or those small ones. So in order for these 2 routers here to communicate, they need to be on a subnet that's shared. Okay, and there are dedicated IP addresses for those subnets here. Okay. All right. So let's break down these addresses a little bit more and reinforce how they work. I mentioned before that IP version 4 has 32-bit addresses. Here's an example of a 32-bit address. These addresses are scarce, and they're distributed by the ICANN. Remember, the International Corporation for Assigned Numbers and Names. This is also the organization that is responsible for DNS names. And so they give IP addresses to different organizations. At first, they were using what's called Class A, Class B, and Class C subnets, which are chunks of IP addresses that either are /8, /16, or /24 subnets. So if you do the math on that, powers of 2 to the 8, 2 to the 16, 2 to the 24, those are blocks of either 256 or 65,000 or 17 million addresses. So they had 3 different sizes of addresses. So if Northwestern wanted IP addresses, it would go to the ICANN, it would make a case, it would say, we need some addresses, give us a chunk. And the ICANN would say, okay, here are, well, maybe 256 is not enough, but here are 65,000 addresses. And Northwestern would say, oh, great, thanks. Northwestern doesn't really need 65,000 addresses, but if it made a request in the early days, it would have gotten those, just because they were using these only these three sizes, like small, medium, and huge, or like small, large, and super huge. So this original design was very wasteful because there wasn't fine-grained control, and organizations could get a ton of addresses they didn't need, or otherwise you'd have to get a bunch of the smaller ones together and give those as a group, and that would be like hard to specify. So nowadays, IP address blocks are distributed using classless intradomain routing. It's called classless because it's not like class A, B, and C anymore. It's just arbitrary numbers for the sizes of the subnets. And this is called CIDR. That's the acronym here, classless intradomain routing. So the ICANN distributes IP address ranges with any power of 2 size. Okay. There's still powers of 2 because you always choose a very specific split between bits that are specifying the subnet and bits that are specifying the particular host on that subnet. So although in the case of an IP address allocation from the ICANN, they're not really, what they're giving you is not a subnet per se, because the machine, probably will deploy a bunch of routers in your organization to split up that chunk, but they're giving you a chunk of addresses. And by changing the low bits, you can basically, all these yellow bits down here are available to you to change to assign different IP addresses to different machines on your network, but all the green bits at the top are the ones that identify your allocation. So this particular sequence is defined as It can be translated into the dotted quad CIDR notation like this. It's a /23 because we can count 23 of these green subnet bits, and then that leaves 9 bits at the bottom. 9 plus 23 is 32, the total. So we have 9 free bits in the bottom, which means how many IP addresses do we have available in this subnet or CIDR block? There are 512, right? 2 to the 9th power. Cool. All right. So those are IP addresses. Fun stuff. Actually, it's a little bit tedious to work with those, but you'll get the hang of it. Now, I mentioned before that routers have forwarding rules, and this diagram kind of shows that each router has its own forwarding rules. And forwarding rules tell a router how to deal with packets based on the destination address, IP address. So the forwarding table is what allows a router to look up, for a given IP address, what do I do with it? And when we say what do I do with it, specifically, which link do I send this packet on? I need to send this packet somewhere when it comes in. Either needs to go into link 1, 2, or 3. And so it'll look up in its forwarding table the address for the destination. It'll find that address, and it'll use the link number that's in that table, right? Very simple lookup. Somehow, the more difficult or interesting question is, how do we determine that forwarding table to begin with? That is what we'll talk about in the next chapter in the control plane and with BGP and so on. But for now, let's just assume the forwarding table is given. So we have rules that decide which link a packet should be sent out on based on the destination IP address. But there are billions of IP version 4 IP addresses, 4 billion in particular, right? 2 to the 32nd power. You don't want to have a table with 4 billion entries. That's too big. It doesn't have to be that big. So what you do is have rules that apply to ranges of addresses, and hope that the ranges are in geographically or network topologically reasonable places. Okay, so we'll see an example of that here. On the bottom here, we have a forwarding table, an example of a forwarding table, just this green table. It specifies a IP address range using the CIDR notation, but I'm drawing it out here with bits and wildcards. These stars are wildcards. It means any address that matches these high bits, and the low bits can be whatever. So that allows for a range of values, right, between all zeros and all ones. That goes to link 1. This other range, which has this prefix and these and whatever you want afterwards, that goes to this other link, and so on, right? So there's prefix matching and rules based on prefix matching are used for forwarding. Okay, and the thing is, you can have overlapping prefixes because the length of the prefixes can be different, right? So for example, rule number 2 and rule number 3 here can both match some of the same packets, right? Because these wildcards, because these rules are different only where in places where there are wildcards in the second one. But the tiebreaker is that longest prefixes are used. So we use prefix matching, and if there is more than one match, we go with the longest prefix. Okay, so if there was a packet that matched the second rule, yes, technically it also would match the third rule, but we would use the second rule as to decide it. And also notice that there's a final rule here, which is wildcard everything. That's a default, and obviously that would match every packet. But we keep this. We have this in case these other rules don't match. So typically what you'd find in a routing table is one default and several or tens, or I don't know. It depends on really how core the router is. If the router's in the core of the internet, you might need a lot of rules. If it's near the edge, then you have fewer choices. And so you might be able to get away with fewer rules being needed. Okay, so I think I said most of what's written here. If we can translate these ranges, which might be insider notation, it could also be written in insider notation, into a range of first address and last address, like shown here. Okay, and also insider notation. So I want you to actually, I can tell you, but before I tell you, why don't you think for a second about how we compute both the first address and the last address in this range and the insider notation, okay, based on these bits in the prefix rule. Well, what you can do is if you plug in all zeros for the wildcards, you get the first address, right? So that would give us this 200.23.16.1.0. That one's kind of clear. For the last address, what do we do? Well, we could plug in all ones. That would be the final address in this range. And that's how we get this number. Notice the 255 is all ones. That's the number right before 2 to the 8th power, which is 256. And then the insider notation is just taking the first address, which we computed before, and then instead of explicitly spelling out the last address, we just take the number, we count the number of specified bits in the beginning, and that is the slash subdomain prefix length. All right. Now, just like with TCP, and also with HTTP, we have headers associated with this protocol, with the IP. So this shows all of them. Let's go through them. At the beginning, we have the version of IP. There's actually you see this is version 4, so there would be a bit sequence to indicate version 4 in here. There's some information about the length of the data that's coming, the length of the header as well, because that can vary. There's an optional part down here, which may or may not be included, so there's a length here to indicate that. There's a set of 4 bytes here in yellow for fragmentation. I'll talk about that in the next slide, so let's not dwell on that yet. This third row is where it becomes interesting. Time to live here is an integer, an 8-bit integer, which says that indicates the maximum number of remaining hops for a packet. So as a packet moves throughout the network, this will be decremented by each router that handles the packet. And the purpose of this is what? You could probably think of it. The purpose of this is to prevent packets from staying in transit, from traveling forever accidentally, because there is accidentally a loop in the routing rules. So if one packet hands it to another, it hands it to another, it hands it to another, it hands it back to the same packet, that would be bad news, because it would just keep flowing. The router would probably make the same decision about where to send it, and so the whole process would be repeated indefinitely, right? The packet would just be flowing around and around. The thing that prevents that is having a TTL, time to live, in this IP header. So every time you initialize it to a reasonable value, like maybe 64, and every time it goes through a router, it gets decremented. When it reaches 0, then the router should drop the packet. There's a little section here to indicate whether the data that follows is TCP or UDP or ICMP or something else. That lets the receiver know how to interpret the data that comes afterwards. There's a checksum, just like we talked about before with UDP and TCP. And then again, importantly, there are two IP addresses, the source address and the destination address. The destination address is needed for the routers look at this to figure out which direction to send the packet. The source is needed for the receiver at the end side to determine which application to give it to or whether to drop it or whatever. Just like the combination of the source IP address and the port number in TCP or UDP will indicate to the receiver what application needs this data. So if we look at the required data here, there are like 1, 2, 3, 4, 5 rows. Each of these rows is 32 bits, which is 4 bytes. So 4 times 5 is 20 bytes. So an IPv4 header is 20 bytes large. TCP also has 20 bytes of header overhead, which we saw last time. So that together gives 40 bytes of header overhead for a TCP IP packet. Okay, so some of the headers I showed you before were dedicated to IP fragmentation, which is actually kind of an obsolete feature. We'll see in IP version 6 that fragmentation is no longer supported, but it is supported in version 4. What this does is it allows the network to have different MTUs, like different maximum packet sizes in the different links. So there's no standard required maximum transmission unit, like packets. There's no standard packet size across the whole internet. In practice, usually it's 1500 bytes. So it's kind of standard, but not technically standard. It's possible for some links to have larger or smaller maximum packet sizes. And to negotiate that, what happens when you have a packet, there has to be some mechanism to deal with changes in maximum packet sizes. So if you have a big packet that's traveling through here and you have this link here that doesn't allow packets of this large size, IP actually has a mechanism for breaking it into pieces and having those pieces be reassembled actually at the receiver, not along the way, although technically they might be reassemblable by this router. We don't want this router to have to remember these packets and do all that work. The receiver will reassemble those pieces into the original large packet. Okay. So this is kind of like what TCP does. One of the purposes of TCP is to take large messages and break them into chunks, into segments, and reassemble them at the destination. But what TCP does is much more sophisticated because it has acknowledgements and retransmissions, and it allows huge messages to be broken into a lot of pieces. When you do that, you need to have a mechanism for dealing with one of the pieces being lost without losing everything, right? IP fragmentation does not have that mechanism. So if any one of these pieces is lost, then the whole packet will be lost. But that's kind of there. So not a big deal, but something you might notice. So to review, why does this router here decide to fragment this packet? What would be the reason for fragmenting this packet? I hope you remember that the reason for doing this is that the packet arrived that's too big for this link it wants to use. So this link out here has a maximum transmission unit or maximum packet size that is smaller than the packet it wants to send. So it needs to break into little pieces. Cool. So there are headers for that, and 3 headers. There's one for the ID of the packet, and a flag to indicate fragmentation, and an offset. So basically, let's start off with an example of a large packet, 4 kilobytes, 4,000 bytes. This is too big for most internet links. So if a router wants to send this, it breaks it into 3 pieces. Each of the pieces has smaller size. In this case, we break it into one of size 1500, another of size 1500, and then a final one of size 1040. So these add up to 3040, but the reason for the additional size is because of repeated header overhead, I guess. Well, I don't know if that quite adds up. But anyway, there's this ID 13, which is used to identify the fact that this is the same packet that needs to be joined together. And the fragmentation flag, if this flag is set here, when this first packet is sent, the fragmentation flag of 1 indicates to the receiver that this is not the whole packet, but there's more coming later. And the offset indicates where in the stream that the next data is. Now notice these offsets are kind of funky, actually. Because they're factors of 8, so you have to multiply the offset by 8 to get the actual byte size of the packet. This is just done to save bits because there's no need to have really precise offset sizes. You can just make everything a multiple of 8 bytes. Yeah. Okay, so if you want to take a quick breather, this would be a good time because we're moving to a slightly different aspect of IP now. The final topic for today is network configuration on an IP network. So in order for a machine, a host, to operate on the internet, on an IP network, it needs to know 4 things, actually. It needs to have an IP address and know what that IP address is. It needs to know the subnet mask. It needs to know the gateway IP address. I'll tell you what that is in a second. And it needs to know an IP address for a DNS server. So these are 4 32-bit numbers. Now, let's go through them one at a time. And actually, you can stop and think for a second whether you know why these things are needed right now. But I'll go through them for you. The first one, you need to know your own IP address because in general, you can't communicate meaningfully on the internet if the person you send a message to can't respond, right? Communication is a two-way thing. So you set a source address on all your outbound messages so the receiver can send a message back to you, and also so that the receiver can identify this message to distinguish it from messages that's getting from other machines on the internet. Okay, that's kind of straightforward. You need to know your own IP address. Great. You need to know that your subnet mask, because you need to decide for every message you want to send whether that message can be sent directly to a neighbor on the subnet, or whether if that machine is not one of your neighbors, it's not on your subnet, in which case you need to send the packet to a router which will forward the packet to the final destination. Okay. So if a receiving, so this is used, the subnet mask is used together with your own IP address to determine whether a particular destination address is a neighbor, in which case you can send the packet directly using link layer MAC addresses. Again, details of that we're not going to cover quite yet. Or if not, if the IP address is outside of, like in other words, you take your own IP address, you apply the subnet mask. If those bits are the same as are different than the destination, that means the destination is outside your subnet. So you need to forward that packet to a router. Okay. Now that should lead you to realize that something else that you need. You need to be in contact with a router in order to forward all these packets that are destined outside the subnet. So the gateway is a term we use in IP configuration to refer to the IP address of the router that you're connected to. So it's a router on your subnet. It has to be on your subnet because you have to be able to send packets to it directly. So that router on your subnet will be, the gateway router, gateway IP address is the router you'll send packets to when they need to be sent to, when the packet needs to be sent outside your network. Now you won't actually use the IP address directly of that gateway. It turns out, we'll see later on, that you will use the IP address just to translate to a MAC address, because you still are, when you're sending a packet outside, you're still going to need that destination IP address to be the IP address destination of the packet. You'll use the gateway MAC address to indicate that just on that first hop it goes to the gateway. But that'll become more clear later. And finally, I say that you need a DNS server IP address. That should be fairly clear. If we want to use host names, domain names, URLs to have domain names in them, we need to be able to translate from host names to IP addresses using DNS. And so we need an IP address for that DNS server so we can send those DNS requests. And those things that will be provided once you have those four. Somehow, you can operate on an IP network. The question is, how do you get those four things? Well, they could be manually configured if you happen to be the person in control of your network and you know all the details. If you're the one who set up the router and the DNS server, and or someone told you, your IT person told you, that when you plug into a certain jack, you should be using a certain IP address and a certain subnet mask and a certain gateway address and a certain DNS server address. You can set that stuff manually. That's typically not done. Instead, what's typically used is the Dynamic Host Configuration Protocol, DHCP. You may have seen that. That's a protocol that allows machines joining a network to make a request to get those parameters. All four of those things. Now, it's a little tricky how that works because I said that you need these things to operate on the network, yet I'm saying there's a network protocol that you use to get those things. Kind of a chicken and egg problem. We'll see DHCP can be used before you're configured for an IP network because it actually operates at the Ethernet layer, or you don't use IP addresses with DHCP. You just use MAC addresses. So you just send these kind of broadcast messages that go to everyone on your subnet. So to simplify DHCP, let's imagine we have a DHCP server here and then a client that's arriving on the network and needs to be configured. It doesn't have an IP address yet. It doesn't know about the DNS server, any of that stuff. But what it can do is it can plug in, when we say plug in, we can either mean physically plug in or connect to a wireless network by supplying the SSID and a password. Either way, let's think of it that's plugging in. And once you plug in, you can broadcast messages. You can send local broadcasts that will be received by everyone in your subnet. So all the nearby machines. Included in that list is a DHCP server. And that DHCP server is going to be listening for these broadcasts from arriving clients who are asking for information about their what IP address they should be using. So the arriving client makes a broadcast asking for the MAC address of a DHCP server. The DHCP server responds with its identity in terms of the MAC address, and it also provides an IP address that the client can use. Now notice that both of these messages go to everyone on the subnet. So for example, if you turn on Wireshark and you're on a busy network, you'll see DHCP discover and offer messages being sent by clients as they come into the network. Because there's no IP address on those messages because the client is not yet configured. And normally the IP address is what distinguishes the particular recipient. The client sends an acknowledgement. In this case, to take that address, it doesn't necessarily need to be a broadcast actually in this case because now it knows the MAC address of the DHCP server, but that's a detail. And a DHCP server acknowledges. So it's kind of a four-way handshake. Really, the first two messages are the most important ones. There's just an acknowledgement so that the DHCP server knows that the IP address it gave out is actually going to be used. Okay. But we'll actually come back to that once we learn more about MAC addresses to see how that really works. So addressing on the internet, I remember in an early lecture I talked about telephone numbers, like old telephone landline phone numbers, and how they were organized in a hierarchical way where you had the country code first and then area code, which in the US would be a state or part of a state, and then like an exchange, and then finally the particular customer. We would like internet addresses to work in the same hierarchical manner because it makes routing easy. It makes the rules for routing easy through route aggregation. Okay. So what does that mean? So let's consider a ISP here. It's called fly-by-night ISP, and it was given by the ICANN a certain block of IP addresses, a /20 block of IP addresses, which is specified here. And what this ISP does is it sells those IP addresses as well as connections to it to 8 different organizations here. It actually has split up this chunk of IP addresses, this block, into 8 pieces. You can tell that it's broken into 8 pieces because the subnets here that I'm showing are they start with the same the first one is the same number, but it's that by adding 3 to the subnet, we add 2 to the 3, which is 8. We break it into 8 pieces. And I guess you have to do a little bit of math to figure out what the correct starting points are for the later organizations. Anyway, by the fact that these organizations are in the IP address space, they're adjacent, like these numbers are next to each other, are consecutive, and their connections are also, they're actually in the network topology, they're kind of nearby, right? They're all connected to the same ISP, which is receiving all of its traffic, all the traffic that eventually will go to these places. So the rules that are needed in the core of the internet are simplified by this aggregation of addresses and the kind of like geographic or network topological co-location or nearby location of these blocks of addresses. Since these are all nearby, instead of having 8 different rules saying that these 8 different blocks of addresses should be sent like to fly-by-night ISP, these can be combined together into a bigger rule that contains all of them and just them, right? So this, we'll talk, actually, what I'm showing here are advertisements, which we'll talk about in the next chapter. But these advertisements are related to the rules. You can think of these as rules for now. There can be a rule that's accepted by the rest of the internet saying that, or the router right here, saying that traffic destined for this /20 block should be sent along this one link. Just one rule instead of 8 different rules. Okay. And longest prefix matching is also used in when deciding the rules of the internet with BGP, which we'll talk about later. So if we have, it's not super important right now to be honest, but if we have 2 different ISPs, let's say 2 different routers that have ways of reaching this organization down here, organization 1, this IP address range is actually contained in both. This fly-by-night ISP can reach all of these, so it might advertise one big chunk that reaches all of them. The second ISP might just have one particular connection, a connection to just one of these 8 down here. So it might advertise some other blocks as well as this particular sub block that organization 1 has. From the rest of the internet's perspective, this specific advertisement, more specific advertisement down here is seen as a better one. So the traffic would tend to flow down through the second ISP because using this longest prefix matching rule. But that's not super important right now. Okay. All right, so we got through a lot of introduction for IP, Internet Protocol, specifically version 4, with those dotted quad style addresses that allow a total of 4 billion different IP addresses. Routing is the task that routers do, unsurprisingly. But what it means is forwarding packets on the network toward their final destination. To do that, each router has a forwarding table. The purpose of that table is to map addresses to outbound links. And those addresses are specified with ranges, not individual addresses. We call that forwarding action of routing of routers the data plane in the IP network, whereas determining the forwarding rules in the first place is called the control plane, which we haven't covered yet. We'll talk about that in a couple more lectures. IP version 4 has this way of fragmenting packets that are too big to pass through a particular link that has a limited packet size. They're reassembled at the destination. Not super important, but it's there. And we introduced the concept of IP subnets, which are important. Those are ranges of addresses that can communicate directly to each other using MAC addresses, but that's not super important. We define subnets with CIDR notation, where we have the first address specified and then slash a number, and that number after the slash is the number of bits that are the same for every address in the subnet. So the bigger this second number is, and this can only be between 0 and 32. The bigger this number is, the smaller the subnet is. So if you have a /32, that means all 32 bits have to be the same for every IP address in the subnet. That means the subnet has only one IP address. A /0 means that none of the bits have to be the same, which means it's the whole internet. So in practice, you find numbers between 1 and 32 for subnets to specify a range of addresses. We also have a different way of specifying subnets, which is called a subnet mask, which is where you take those high bits and translate them into ones and then put zeros afterwards and translate it into the dotted quad notation like you see here, 255.255.255.240. That's the same as a /28 subnet, because 240 is the number you get when you have the bits 11110000 and you translate that into binary. Okay. To operate on an IP network, a host needs four things: an IP address, the subnet mask, the IP address of the gateway, and the IP address of a DNS server. That fourth one technically is not necessary because you don't need to use host names necessarily, but in practice you really do want to use that. It's a pretty important feature of the internet. The gateway is the IP address of the router on your subnet that will accept packets from you and forward them to the rest of the internet. In other words, forward those packets to IP addresses that are outside your subnet. And DHCP is the protocol that allows newly arriving machines to request this IP configuration, which is to say, to get these four numbers from a router nearby. Okay, cool. So that's IP. We'll be talking about IP version 6 next time, and NATs, and then after that we'll move on to the control plane again. For continuing the discussion of routing. All right, see you later.